Hola! Welcome back to Relativity, the head-spinning world of relativity, where we look at all of the craziness that exists when things move close to the speed of light. Last video we talked about time dilation. We said the single moving clock runs slow, or in terms of our math, that two clocks record a longer time than one clock. Today, or in this video, we are going to look at something called length contraction, which we can summarize in a simple statement and say moving things are skinny. So before I jump into sort of showing you how the calculations work, because they're really easy, just like they were really easy for time dilation, I'm going to offer you a couple of different ways that you can measure the length of something. And there are some terribly misleading names, just like those misleading names we saw with time. So proper length, which sounds like it's maybe the correct way to measure the length of something, which is L with a little circle, which means not. You don't need to know that. It doesn't matter. Is the length measured when an object is at rest beside two people? Like a school bus is sitting in front of the school and it's not moving. And so Susie and Jimmy grab a measuring tape, and one person stands at the back of the bus and the other person walks towards the front of the bus. Two people, stationary object. You simply grab your tape measure, you measure the length. Done. So some people call that proper length. Rest length is maybe a better name because it's the length when the thing is at rest. There is also another term, the improper length. Sounds like it's somehow wrong, but it's not, right? It's just a different point of view. It's just a different way to measure. And that would be like maybe measuring the length of that school bus when it's moving past you. So the length measured by one person when that object moves past them, or when you move past that object. Now, if we take that school bus and we move it past you at 3/4 of the speed of light, like 0.75 c, I have no idea how you would measure that. But if you could measure the length of something ripping by you, we would call that the improper length. Again, it doesn't mean that it's wrong. It's just a terrible name. So we're actually not really going to worry about remembering those definitions. We're just going to call things length. And I'll offer you a different way to think about it. So let's go back to that picture, the flight to Vancouver that we talked about in the last video. Now remember what we said in the last video, looking at the whole recording time with the clock's information. We said that the pilot's clock is going to record, their time is going to be short. The single moving clock runs slow, right? It's short, it's small, something like that. And then we said that people who stick around on the ground with their synchronized clocks, the observers, the plural, they record a longer amount of time. Or a larger amount of time. Call it whatever you want. It doesn't really matter. Now, if we go back to the simple D equals V times T that we chatted about in the last video, and we think about, okay, there's a short time and a longer time, and we go back to that equation. Maybe I'll scribble it down here on the side. D equals V times T. Remember, everybody agrees on the velocity that things are moving, so we agree on that. But we disagree. The 2 points of view disagree about the amount of time that goes by. One person, the pilot, says it's short. The people on the ground, the observers, say it's long. So that means you have to also disagree about the distance, right? The length. You have to. So what ends up happening here is, from the pilot's point of view, a short or small time is going to give you a short or small distance. We had said, hey, that another way to say short or small was to call it skinny. Whereas the people who stick around on the ground, they are going to measure. They measure a long time or a larger distance. Or sorry, longer time or larger time. They're going to measure a longer distance or larger distance, whatever descriptor you want to put in there. So here's what I mean by that. Here's the sort of the story. So let's say, I don't know if planes have odometers. So maybe let's actually switch gears if this is okay. Remember, they're all just thought experiments anyway. Let's switch gears, and instead of thinking about an airplane trip, let's think about a drive. So if you drive to Vancouver, or walk, or go like at regular speeds, which is basically not moving, right? I think a trip to Vancouver, from Penticton to Vancouver, is probably about 450 kilometers to get yourself to downtown Vancouver. If you could go really fast, if you could go like close to the speed of light fast, relativity speeds, half the speed of light, 3/4 the speed of light, 90% the speed of light, something fun, you could get to Vancouver very quickly, not only because you're moving quickly, but because the distance between Penticton and Vancouver shrinks the faster you go, right? It has to shrink. So what's crazy is these people on the ground, if they're like, hey, you know what? How far is it from Penticton to Vancouver? The observers on the ground, this point of view here, they might say that the distance from Penticton to Vancouver is 450 kilometers. Maybe they've got a really long measuring tape, right? And they measure it. One person in Penticton, the other person rides their bike or walks or runs or drives all the way down to Vancouver with the other end of the measuring tape, 450 kilometers. The pilot flies to Vancouver, or drives, maybe we should say that the driver goes to Vancouver really fast, like relativity fast. They may say that, hey, I got from Penticton to Vancouver, not in 450 kilometers. I look at my my odometer. I got there in only 200 kilometers. I'm just picking that number out of thin air. Now, this disagreement is real, right? If you could go that fast, the distances would actually shrink for the single moving clock. So it's not that the person going fast thinks they only traveled 200 kilometers. They did travel 200 kilometers. And it's not that the people who sort of just went slowly or walked measured 450 kilometers, or they think it's 450 kilometers. It is 450 kilometers. So how far is it from Penticton to Vancouver? Is it 450 kilometers or is it 200 kilometers? Yes, it is. Right? It's actually both. It depends on which point of view you're measuring from. So I'll skip that. The results is moving objects are shorter. Now here's what's kind of crazy. If you were that person in the car driving at close to relativity speed, and you could somehow get to Vancouver in only 200 kilometers, that means everything that you pass along the way is also going to be skinny or shorter. So if you're ripping through like Manning Park and you see a group of Girl Scouts getting ready to go for a walk, as you go past them, if you were going regular speed, they would look normal, right? At regular speeds that we drive, nothing is exciting, distances don't shrink. Gamma's just too darn small. But if you can get gamma up into the exciting values like 2 or 5 or 20, then that means everything you pass along the way is going to be 2 or 5 or 20 times skinnier. Not just look 2 or 5 or 20 times skinnier, but be 2 or 5 or 20 times skinnier. So this car drives past the people at regular speed and goes, that wasn't very fun. So maybe they turn around, they back up, and now the race car pins it, right? They're going to go way faster. They go some value or some speed that gives them a gamma value of 2. And as they go by these people getting ready for their nature walk, that's what the person in the car would see, right? He would see the people as being skinny because they are skinny. It is not an optical illusion. They are actually skinny. And if the guy in the car goes, that's kind of funny, like those people got skinny, and he turns around and he goes past them again even faster, they would be even skinnier. In fact, what could potentially happen, these are just weird thought experiments, right? Is if you went fast enough, you could almost make these people like two-dimensional. They'd be like Flat Stanley. You could get it to that point where that person in the car is moving so fast past these people and all the trees and everything else they pass along the way would shrink by a factor of gamma and become that skinny. Now, sometimes people look and they go, well, Mr. Heinrich, that would like kill these people getting ready for their nature walk. But it actually doesn't kill them. They're totally fine, because I want you to think about the flip side. If you asked these people, if you said, hey, are you skinny? Those people would say, no. Because in their point of view, they would look totally normal. And maybe you can see where I'm going with this. They would say, no, we're not skinny. But we did just see this really funny, skinny little car go by. So when we shrunk these people here, that was the point of view of the driver of the car, right? They got skinny, those people on the side of the road. Well, for the people on the side of the road, when they see the car go by, just the single car, all the trees, everything else, the environment looks normal, but that single car going by, ripping by, if it's going fast, it might look like that. If it's going really, really fast, it might look like that. And if it's going really, 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 really fast, it might look like that when it goes by. And it looks like that as it drives by because it is like that as it drives by, right? It is skinny. It doesn't just look skinny. Again, not an optical illusion. It actually is skinny. So it actually is kind of cool. It works both ways. For the people getting ready for their nature walk, just the car would look skinny. But for the person in the car, if they're driving really, really fast, everything outside of the car would be skinny, right? The people, the trees you drive by, Manning Park Lodge, it would be skinny. Other cars passing by the other way would be skinny. His car would look normal. He would look normal in his point of view, but everything outside of the car would be skinny. So that's length contraction. It's crazy. What's really, really cool is it makes things like traveling through space sort of more possible if we could go that fast. Because if you think about other planets and stars being really, really far away, if you could go close to the speed of light, not only are you going to get there quickly or quicker just because you're traveling so darn fast, but the distance between you and those distant stars or planets shrinks when you go fast. It shrinks by a factor of gamma. So it's actually sort of working out both ways for you. You're going really fast, and you actually don't have to cover as much distance because distance is shrinking. So a super cool concept. Life would be very strange, though, if this happened, right? Like driving to Vancouver, if everything you saw around you was skinny until you stopped and then everything would go back to normal, it would be very, very strange. So let me show you what the math looks like. There's the equation on your formula sheet. I don't want you to worry about that equation. We are simply going to do this. As sort of the math equation, remember for time, we did 2 clocks are bigger than 1 clock. For length, I want you to just remember this. Moving equals skinny. And I'll show you what that looks like as we apply it to a couple of questions. I do want you to keep in mind that objects never get longer. So when an object is stationary compared to you, that's the longest it ever gets. So when you go and look at the school bus that's parked in the loop in front of the school, it's never going to get longer than that. But if that bus were moving really, really fast compared to you, you could make it skinnier. The other thing is only things in line with your velocity are impacted. So for the car driving past those people, anything that's sort of beside the car gets skinny. So that distance, Vancouver, that distance shrinks, but vertical distances don't shrink. So if you're moving horizontally, maybe this will make more sense. If you're moving horizontally, horizontal distances shrink. But it's not like the bird flying in the sky is somehow skinnier, right? Or closer to you. So vertical things aren't impacted unless you're moving vertically. Let's try out an example. Again, crazy concepts that I hope you can join me and we can chat about on Zoom, because I'd love to hear you bargain with me and run some ideas past me. And I'll run some new stuff past you as well that I just can't fit in this video. But let's see a couple of math examples that I think you'll like. So let's try this out. A plane has a rest length of 24 meters. How long is it as it passes an observer on the ground if it's traveling at 60% the speed of light? So here's what you have to do. You have to figure out whose point of view you're measuring from in these questions. So it says, how long will it be measured to be as it passes an observer on the ground if it's traveling at 60% the speed of light? So if you're the observer on the ground and this airplane is moving past you, I guess we first have to answer this question. Is the airplane moving compared to that person on the ground? And you would say, well, yes, it is. And if you answer yes, we know that moving things are skinny. And you might be sort of watching this going, well, who would say that the plane isn't moving? And it turns out if you asked anybody inside of the plane, are you moving compared to the plane? They would say no. They'd say, well, maybe we're moving compared to the ground, but no. I'm just sitting in the plane, so the plane isn't moving compared to me. So that's the other point of view, right? The plane would look normal to people sitting in the plane. The plane will look skinny to everybody that's outside of the plane. All of us that are observing from the ground. So in this case, we have to make the plane skinny because we're outside of the plane. And we know that it's moving compared to us, so it's going to look skinny because it is skinny. All we need to do is the same thing we did for time, where we play the beta-gamma game. So beta is actually sitting right there. Super quick to get. So beta is 0.600. If we turn that into a gamma value, remember gamma is 1 over the square root of 1 minus beta squared. Got my calculator here. Let's see what it says. 1 divided by square root of 1 minus, beta squared, 1.25. So that means the length of this airplane, according to the observers on the ground anyways, the length of the airplane will be the rest length of 24 meters. And here we're trying to make it skinny, so we simply divide by gamma. That's it. So a nice, easy calculation. 19.2 meters. So that's how long the plane is according to anybody that's not on the plane. That's anybody who's outside of the plane. So if you're outside of the plane and it's moving past you, you're going to measure that plane at 19.2 meters. If you're on the plane, remember some people would actually say 24 meters. That would be the length according to anybody that's inside the plane, because they're moving with the plane, so the plane looks totally normal. So there's your 2 points of view. One is normal or at rest. That's the dark blue. And then one would be that moving skinny length, which is for anybody outside the plane. So just like time, we can just sort of play around with multiplying or dividing by gamma. So we'll scroll through all that. Okay, let's try some other questions here. A train moving at 40% the speed of light passes by a car waiting at a train crossing. Dan, who's driving the car, notices that it takes 12 microseconds. That little prefix there is micro. It takes 12 microseconds for the train to go by. So here's our little picture. We've got Dan, a single person with a single clock waiting at the train crossing. got a fancy little BMW race car. And then we've got this long relativity train moving really fast, 40% the speed of light fast, captained by Tina, and Tanis is in the caboose. And here's what we're going to try to find first. There's actually 3 things we're going to find in this question. What is the length according to Dan? And you might look and go, okay, I got this. It's just like the last example. You take a length that's been given to you, and you figure out whether you need to make it bigger or smaller just by either multiplying or dividing by gamma. And then you sort of look back at the question, you're looking around up here, and you realize, oh, like I don't see a length. What's going on here, Heinrich? How do you find a length if you're not given a length? Like, you can't multiply or divide by gamma if there's no number to work with in the first place. If you ever run into this situation where you're trying to find a length, but you haven't been given a length, it also works for time. If you're being asked to find a time, but you haven't been given a time, it turns out there's another equation we can use. We've used it a few times already. It works great. And some of you, I think, are probably sitting there going, I know what it is. We can use d equals v times t to solve for the d, right? What length does Dan measure the train to be? Well, we know the velocity, and we know the time according to Dan. So we can take those 2 values, we can play around with units, we do have to watch that, but then we can multiply the 2 together and we can solve for d. So what we're going to have to do with velocity, this equation works great, but your velocity has to be in meters per second. Your time will have to then be in seconds. So we do have to watch our units in this case. Remember to get 40% the speed of light into meters per second. We do exactly actually what it's telling us to do, which is take 0.40 and multiply by the speed of light. So that's going to be 1.2 times 10 to the 8 meters per second. I'm just going to put the units on there just so we can see that we've changed it. And then 12 microseconds, the easiest way to get that into seconds, you can go to your formula sheet and you can see that the exponent on micro is 10 to the minus 6. I tried to come up with a semi-realistic amount of time for how long it would take for a train to go past you if it was traveling at 40% the speed of light. And if we throw those numbers into our calculator, times 12, exponent negative 6, that train, according to Dan, is 1,440. We'll go with chemistry rounding there, m for meters. So there is the length according to Dan. So that's part A. Let's see what else we've got. Part B, according to Tina and Tanis on the train, how much time does it take to go by Dan? Okay, now we're talking about time. And we know with time from last day's lesson that we don't worry about the equation on the formula sheet. We know that instead 2 clocks record more time than 1 clock. And here it's kind of cool. We've already been given the 12 microseconds according to Dan. That's the 1 clock time. Right? Dan's just sitting there with a single watch. So for us to find time, we are going to simply take the 12 microseconds and we're going to multiply by gamma. Which means we just have to figure out what gamma is. Super easy. So we'll do that off on the side here. Beta is sitting right there in the velocity, which is kind of cool. 0.40. And if we go to turn that into a gamma value, I'm not even going to show the calculation. I'll just do it on my calculator here. We get a weirdness factor of 1.091. So in this case, to find time, we're almost there. This one's quick. It's 12 microseconds multiplied by, I'm just going to leave it in microseconds, right? It doesn't matter what the units are here. Times 1.091. The amount of time, according to Tina and Tanis, those observers on the train, is 13.1 microseconds. There's part B. Sort of last day's lesson. And then let's try part C. According to Tina and Tanis, how long is their train? It's actually the last thing we need to find. The only bit of information we don't know about this scenario is how long is the train according to people on the train. We know that Dan thinks it's 1,440 meters, but remember that Dan is going to see it as skinny because the train is moving compared to Dan. The train is not moving compared to Tina and Tanis. Right? It's moving compared to the ground, but not compared to them. Now, it turns out there's actually two options here for how you can solve this question, now that we have all the other information. Either option is equally good. I'm just going to go through both of them quickly. One of the options is to use d equals v times t. The only thing you have to be a little bit careful of is this is now the point of view of Tina and Tanis. So we have to use the amount of time that they said it takes to get by Dan. So if we're going to run this equation, the velocity we had said in meters per second was 1.2 times 10 to the 8. And then we just found the time according to Tina and Tanis. It was 13.1 microseconds. So if we multiply those two things in our calculator, (13.1 times 10 to the negative 6 times 1.2 times 10 to the 8. We should get something bigger than 1440 because remember, Tina and Tanis are going to measure a longer length because they're not moving compared to the train. So they see it as normal, not as skinny. There you go, 1572. I'm just going to leave the rounding, pardon the sig figs, just for comparison's sake here, so we can compare it to 1440. The other option is we can actually use beta and gamma. We can play this game. We can say, hey, according to Tina and Tanis, is the train moving compared to them? And you'd say, well, it's moving compared to the ground, but it's actually not moving compared to Tina and Tanis. So we'd say no. And if something isn't moving, it's long. It's normal, and I'm saying that in air quotes, right? It's not skinny, so it's long. So what we could do here is we could say, well, beta was 0.4, the gamma was 1. I've forgotten, I think it's on the calculator. 1.091. So why don't we just take the skinny length that Dan measured and multiply by our weirdness factor to make the thing longer. And this option works too. 1.091 times 1440 equals 1571. Now they're both a little bit different, those numbers, but that's actually just due to rounding. Both of those numbers or calculations have some rounded values in there. There was some rounding there, and there was some rounding there, and probably even a little rounding to get that. Although that one might be okay. So don't sweat that they're very slightly different. That would totally slide on a quiz or a test. But there's another way that we can sort of play around with calculating times and lengths. Now, again, I apologize. These videos are kind of long, but hey, we normally do this in 80 minutes, right? Or over 80 minutes. I've got one last question for you. Some slightly different math, actually. And I want to go through this with you because some people get stuck in the algebra. What if we have to work backwards? I think you're ready for this now. At what speed will a 1,570 meter train be only 1,256 meters long? So I'm actually giving you the long length. I'm giving you the skinny length, and I want you to go backwards and find velocity. And typically we would go the other way. I'd give you one length, I'd give you the velocity, you would then find gamma, and then you would either multiply or divide by gamma. So in this case, we can actually get gamma. Gamma is going to be equal to one of those numbers divided by the other. And I want you to think about gamma a little bit. Is gamma bigger than 1 or smaller than 1? And hopefully you're using that pause to go, no, I remember all the calculations we've done. Gamma is always bigger than 1. And it is. Beta is less than 1. Beta is always a fraction of the speed of light, but gamma is always greater than 1. So in this case, if you want to take two lengths or two times or two numbers and get gamma, it's always the bigger one divided by the smaller one. And I think this is going to give us a number we've seen before. Just pretend you don't know what the speed is, because I think this is actually on your worksheet, to be honest. Yeah, 1.25. So let's pretend you don't know or don't have a sheet where you could just go, oh, I've already done that calculation, Mr. Heinrich. It's going this fast. Because I'm very likely going to put one of these on your chapter test, and it'll be some random number, right? Not a nice beta, or sorry, not a nice gamma value that you can just look up on your sheet. So now we have to take that gamma value, and we are going to turn it into a beta. Because remember, what we can do with beta is to get it into a velocity, you can just tack a c on there, right? Just put a c after the number. So let's say gamma is equal to 1 over the square root of 1 minus beta squared. Now what we have to do is a little bit of algebra. We're going to solve for beta. So what we want to do in this case is multiply both sides by the denominator of this fraction. So both sides are going to get multiplied by 1 minus beta squared. That's going to cancel out on that side and leave us with 1.25 times root 1 minus beta squared equals simply 1. And we're wanting to sort of get that beta squared by itself at some point. So I think the next best step would be to divide out the 1.25. So it cancels there on the left-hand side. Let's see what that gives us on the right-hand side. Let's go to our calculator. 1 divided by 1.25 is 0.8. So we're left with root 1 minus beta squared equals 0.8. Now we want to get rid of that radical, the square root. So we can square both sides at this point. Squaring that left-hand side is going to get rid of the whole square root, and then we square the 0.8. That's going to leave us with 1 minus beta squared equals 0.8 squared is 0.64. And if it's okay with you, I'm going to roll up here. Sorry, running out of space. Now what we want to do, maybe I'll rewrite that. 1 minus beta squared equals 0.64. Now I've got this negative beta squared, and I know I'm going to have to take the square root at some point. Probably my last algebraic step. And I'd really like that beta squared to be positive. So I'm going to add it to both sides. Cancel, cancel. 1 equals 0.64 plus beta squared. And now we can subtract off 0.64 from both sides. Get that beta squared by itself. That's going to be 0.36 equals beta squared. And the last algebraic step, square root that sucker. And we've got to get our sig figs here. That is going to give us 0.60 is equal to beta. Now that technically at this moment is not quite a velocity, but we can get it there really, really fast. To turn that into a velocity, remember, I think the easiest thing to do is take that beta value, get our two sig figs, and you can simply just tack on that c. So the velocity of this train is 60% the speed of light. Or if you prefer, you can turn that into meters per second by actually taking 0.60 times the speed of light, times 3 exponent 8. So if you'd rather, you could also list it as 1.8 times 10 to the 8 meters per second. I don't really care, and this one didn't specify, right? So either of those velocities works. So there is lesson number 2. Hopefully the math is okay, right? Crazy concept that when you go fast, distances shrink, but the math that goes with it is nice. So that's the trade. Your homework, your practice that goes with this lesson is worksheet 1. And there's only a couple of questions actually. It's worksheet 1, numbers 5 through 7. And they're actually just like the 3 examples we did here in this video. So give that a try. Check your answers. The key is posted online in the All Resources folder with the worksheet. And again, hopefully you can join me on Zoom because I'd love to answer any questions about this kind of math or the math we've done in this lesson. And I'd really love to chat with you and bargain with you and see what kind of crazy things your brain is coming up with about time dilation and length contraction. So I hope to chat with you very soon. Have fun.